Nonlinear regression model discussion. Yesterday we stopped in problem 4. From there on we'll progress today. So we were talking about estimating a linear consumption function. We did that part. We actually completed up until a and b, so you need to do test of hypothesis whether beta 2 is 1 or beta 2 not equals 1. So we're going to do LR world and LM test on the consumption function. So to begin with, we will move into NLS contest because NLS contest is completed. Just to revise very quickly, testing LR world and LM test in nonlinear consumption function. Whether the null is beta 2 equals 1, alternative beta 2 not equals 1 for t equals 200 observation. We have two parameters theta naught and theta 1, which we are to estimate in theta naught, which is z1 and z2. Basically we are estimating z1 and z2 as we said earlier, and for theta naught representing z1 we have beta 1 yt. So the consumption function was et minus beta naught minus beta 1 yt beta 2. So first of all we have beta 1 yt, and for z2 log L theta 1, everything with everything else we just have y2 beta 2. So our problem is either beta 2 equals 1 or beta 2 not equals 1. So in the first model, which is a restricted model, we don't have beta 2. In the second model, which is an unrestricted model, we have beta 2. And after concentrating the log likelihood for theta naught and theta 1, you see because we don't have a beta 2, so this is beta naught, beta 1 and beta 2 is 1. For unrestricted we have a value for beta 2. And then we'll just go through the equations related to world test, LM test and LR test to do the testing. Okay, so let's have a look into the problem. Do you have any local functions? Yes, we'll start with the local function. So we have how many parameters in the unknown parameters in our equation? We have beta naught, beta 1, beta 2. So b, ct, yt, we have the consumption parameter ct, b and yt. For the constrained model, let's just estimate this parameter. Well, t is length of ct, e is ct minus b1 minus beta 2 yt, which is the equation. This is the sigma standard deviation, which is u prime divided by u transpose divided by t. So the log likelihood function is simply minus 0.5 log 2 pi minus 0.5 log sigma square minus 0.5 u transpose divided by sigma square, or u square divided by sigma square. U square divided by sigma square. That is the very simplest concentrated log likelihood function, concentrating out the residual, and LF is minus f. So how do you do it in R? We do it in the same manner for the constrained model. Okay, there is no simulation here. Just to start with, there is no simulation. So we are estimating b beta consumption function ct and yt. T is length of ct, fine, is the equation of the consumption function with taking residual on the left hand side. Then we are doing the sigma standard deviation, transpose of e multiplied to e divided by t. Then we have the log likelihood function that we are estimating, and just negative mean and return LF. We want this function to return LF, so log likelihood function. Now with the unconstrained model, we want to estimate beta 3 as well. BCT, see, we didn't have beta 3 here, so beta 2 yt to the power beta 3, which is beta 1 yt, so ct minus beta 1 minus beta 2 yt to the power beta 3, which is b2 actually, from the equation, coming from this equation. So just like before, everything else remains same. Residual u square divided by t, and again the log likelihood function is u square divided by sigma square. Fine, and this is the log likelihood function. And log likelihood function of constraint model at each observation. So in the constraint model at each observation, the log likelihood function log lt minus 1 is bit ctyt. Everything else remains same. We use the concentrated unconstrained model equation here. We actually use the complete equation. In short, we use the complete equation. And here it is, return LF. Okay, now let's move into the equation model itself. We include the model in a function. So first let's load the data. So y is where income goes in, city is the consumption function that's going in. So basically here how we are loading is that the first column of US data goes to consumption, the second column, which is income column, goes to income. So then we transfer income to Y and consumption to C. To C. Okay. Okay, after that we take t, which is length of y, then we estimate the constraint model. Simply we estimate the constraint model with constraint model calling our functions. So you see from the question we have given b0, which is minus 228 minus just 0.9, okay, which basically is coming from our previous well, estimations here, minus 228 minus 0.9 and just 0.9. So theta naught, we want theta naught to estimate, and also the log likelihood functions value. So we want theta naught and the log likelihood function value. Yeah, we want this and the value of this. So fn at b neg log naught, which is the constraint model, b ctyt, just calling the function, and this is the initialization beta naught, initializing the optimization. And here again we pass in the first stage we pass in the values to beta naught, then est results. Here we are gonna store our values, optim, par, this is the par value, which is the initial value, which will be replaced with the final values. Function neg log naught, then ct equals ct, yt equals yt, things where in ct will be stored, in yt will be stored. Method is nilder mid. Not necessarily we need to mention a method and yeah, we are doing nilder mid method. In generally we do Newton-Raphson or Gauss Newton, but here we are not doing that. So we are just doing ultimate, trying a different method. So in theta naught goes the power values from these, and f naught goes just the values. Beautiful. Then displays concatenate and display, which starts with a oblique n, ends with an l oblique n. So in theta naught we have the theta naught's value and 1. So combine theta naught or column theta naught and 1 in columns, and so concatenate and display is simply again theta naught is being displayed, so that we get a structure similar to this. See, we want everything in columns. And then the unconstrained model, beta naught is taking theta naught's values for the unconstrained model. So we are initializing from theta naught here. Okay, and that's an important point here. We are initializing from theta naught values, unrestricted theta naught. And theta 1 f1 is again well, fn in arc, fn in search. This is minimization, this is optimization. They run the same, they are the same actually, because as you can see in constraint it remains same, nothing changes. The optim command remains same. So we call the function, and in f0 and in f1 we have the negative logarithmic function values stored. Fine. So we have theta 1 f1, theta naught f0, where we took theta naught's values as the update or initial values for unconstrained model, and we want to compute the relevant matrices like gradient. We'll need gradient, and we will need OPG, outer product gradients. We need Hessian. So numeric gradient, we call the numeric gradient function numeric gradient. Here is also the same numeric gradient for R. So from we are calling the gradient from constrained or unconstrained model. No, we are calling the gradient from log likelihood function of constrained model at each observation. Functions of constrained model at each observation, basically the whole we want the whole function at each observation. So yeah, that is something to remember. We are calling this function. And optimization, well, the initial value is theta naught in columns, and we want that for ct and yt. Our variables are unknowns are ct and yt. Theta naught ct yt, okay, fine. G is mean of G. Well, we are doing row bind. In G is we are by row we are expressing the column means of G. So column means, these are coming in columns, so the means of G of columns are moved into our into rows of in one column in G. So you see row bind column means of G. Then J is simply GG transpose, because G itself is a matrix. Here we are taking the means of each column and they're all putting in one column with row bind, and this is transpose of G multiplied to G divided by T. Inverse of Hessian is simply calculating numeric Hessian, where theta naught, we are talking about theta naught transpose here for gradient. unconstrained, and yeah, restricted model. We are using theta 1 transpose for Hessian, which is the unrestricted model. Unrestricted model by calling neglog 1. You see, neglog 1 from the unrestricted or unconstrained model. Okay, so inverse of Hessian is coming from unconstrained, while gradient was coming from constraint model. And there you have inverse of Hessian. So theta 1 is unrestricted parameter estimate. Covariance matrix is inverse of Hessian divided by t. Diagonally located is the square root. If we do square root of the diagonal elements of this covariance matrix, we have standard errors. Yeah, well, there you go. And then we do the ratio test, because we need both likelihood and unrestricted and restricted likelihood values. Likelihood ratio test is minus 2t, f0 minus f1. Fine, starts with an n, ends with an n, so t into f0. Restricted likelihood function, unrestricted likelihood function, t into f1. LR test is this, and probability value is 1 minus CDF, cumulative distribution function CDF in chi-square. We want to run chi-square taking the LR test and degrees of freedom 1. P chi-square, here it is much easier. 1 minus, simply instead of 1 minus cumulative distribution function, here in R it is p chi-square. We're not having to do this thing. Instead of, we're replacing this part with p chi-square. Likelihood ratio test of this equation, basically this is the equation on which we are finding chi-square with 1 degrees of freedom. Fine. Then wall test, because we are testing for beta 2, so 0, 0, 1, and beta 2 is either 1 or not equals 1, so q equals 1. So we're doing a row bind, so they're coming in rows, basically in rows side by side. 0, 0, 1 row bind, combine 0, 0, 1. Theta 1, in theta 1 we put row bind of theta 1 in rows, q equals 1, so t r into theta 1 transpose minus q, well, t into t r t theta 1. Oh, this is transpose, the whole thing is transposed. Transpose of r into transpose of theta 1 minus q. Theta 1 was presented theta 1 was probably presented in rows, that is being converted to a column vector. That's why we're doing this. Row bind should basically bind stuff in rows. What is still we can check what is row bind. Combine R objects by rows or columns. C bind. So by columns, row bind is obviously by rows, and column binds is obviously by columns. So basically by rows and by columns, nothing to be confused here. Let's just cross it out. Let's see. Okay. So theta 1, we are converting theta 1 transpose into, because R is in rows, so rows and columns don't go, so we want this to be in theta 1 transpose, because theta 1 was, just have a look, is in columns or in rows. Theta 0 is probably in column. Theta 1 was, see, this one was in row. Theta 1 was in columns. Now this one also was in columns. Theta 0 was also in columns, but they have been displayed in rows. So theta 1 is in columns. Now they are being transported into rows so that we can multiply R and theta, so that dimensionality issue doesn't become a problem. If there is any problem in any error, will show, and you can just change the dimension, not a big deal. So transpose of theta 1 minus q multiplied to inverse of R into inverse of Hessian into R transpose, just the equation. World statistic and p chi-square w1 of w and then 1. So Wald test, this was Wald test, and then LM or OPG, Lagrangian multiplier test, is T G inverse J and multiplied to transpose of G, and then 1 minus chi-square. So two-step LM test. Okay, so this is how it is. In case of a two-step LM test, first we need to have X with income, Y is constant, that we do regression. Okay, this is by calculating Z1 and Z2. Regression, find errors, then you have beta values where B and 1. So we do regression, residual, then we basically these are in columns, so we combine B and 1 in columns. Fine. Then evaluate derivatives at constraint estimates. Z1 is 1s, Z2 is income to the power beta 3, then Z3 is simply the equation beta 2 into log income into income of beta 3, which is basically, after doing this, well, p-value restriction is rejected. We're doing this beta 1, beta 2, y2, beta 2 minus 1 minus beta 1. What we're doing is to consume in the example marginal propensity to consume, the value of which change over time as it is a function of income by yt. Testing the restriction that marginal propensity to consume is constant does not depend on any, involves testing the hypothesis. Define q equals 0, and this is the marginal propensity to consume. Okay, this is the convenient form, not nonlinear regression. So this is the regular LM test, and I think this is the two-step LM test here, TR square. So TR square, right? So first what we need here, we need ZT and ZT transpose, so that we can replace these with these. ZT transpose. Z3 is beta 2 log of income into income to the power beta 3, beta 2 log of income, beta 2 yt, beta 2 minus 1, beta 1 yt, beta minus 1 plus beta 2. Okay, so 1's t1 income, beta 3, Z3 is beta 2 log of income to the power beta 3. These are coming from the constraint estimates. So 0 first is ones, not zeros, ones. Okay, because there's a negative one that replaces everything with here. Beta 2 y income to the power first ones, then income to the power of beta 3, break it out. Okay, then beta 2 log of income into income to the power beta 3. So just look into this. Okay, first we take ones out, then we take the second element beta 2 income to the power beta 3, then we take the third element b2 into log of income into income to the power beta 3. Then in rows we have z, z1, z2, z3 values. Fine. Second step is the residual v equals e mu minus z into z by e. See, z into z by e, or must be somewhere here. So this is it. R square is 1 minus e into e. Z into z by e, right? R square. Okay, so let's see v. E mu minus z into z by e, e z into z divided by e transpose into e divided by v transpose into v. From here basically r square is what? R square is z transpose divided by this portion. Okay, mu square, first is mu square, v is, okay, this is a short form of this equation basically, nothing else, because you have z you have e residual, correct. So this is the this was the equation. So basically just replace this part with this. We have to do it pen and paper again if we want to see how this goes. This was the equation. Regress mu on z1t z2t. Second step regression. Regress mu on z1t z2t and z3t. Fine. R square. Evaluate and compute R square. Twostep LM statistics. Okay. Okay, let's see how this is done in R. We just need to rewrite that equation, nothing else. E, regress E on residual on Z. This is the step. Regress U on Z. Okay, and V, then we have V, which is E minus Z and the regressed value, E minus Z into the regressed value of Z. Okay, E minus Z into the regressed value of Z. So we are updating the information Z with the regress value of Z. So V is an update, being updated, and R square is 1 minus this one regressed on this one. Alright, 1 minus updated Z is regressed on this one. A different type of form. What is the similarity? So what we are doing here, first we're updating with U being regressed. So first we are updating, this is regression, so first we are updating U regressed on Z. Then we are using the regressed value to regress U's on Z's and find R square. So U's and Z's, you take, cross this off, right? You just cross this off. You have Z T Z T transpose, Z T Z T transpose, or you can take the whole thing to represent, yeah, U's and Z's to regress to 2A regression, second step regression. Here we are just doing 2 regressions. That's all. We generally don't need to do a 2-step LM statistics because this problem wanted us to do that. That's why we're doing it. Now the next problem. Now we're gonna move into the next problem. The next problem is NLS regression. Regression 1. Consider the nonlinear regression model YT 1 minus 60 minus theta ut, in which YT is the dependent variable, X is the exogenous variable, and U is the disturbance term. Derive the log likelihood function, the gradient and the Hessian and the information matrix. Find, simulate t equals 100 observation on YT and XT where theta equals 2. The exogenous variable is IID with uniform distribution, which is in between 0 and 1. 2 mean and 3 is the variance. Perform one step of the scoring algorithm with starting value theta naught. Scoring algorithm is simply taking the inverse of Hessian and transforming it to information matrix or OPG. That's it. With theta naught, starting value theta naught equals 1.5. Compute the maximum likelihood estimates using Newton-Raphson algorithm with starting values theta naught equals 1.5. Compare the performance of this algorithm with the Newton-Raphson and BH3 algorithms in terms of iterations needed to achieve convergence. Okay, let's see how this is gonna go. Nonlinear regression. So we are gonna look into this equation here. First we see if there is any local functions. Yes, there's just one log likelihood function, which is because in our problem we have B theta being represented by theta, Y and X. So b, y and x, m equals y by x minus b, m equals 1 by x minus b. This is the equation part where b represents theta. 1 divided by x minus b. You see, in R we don't do element by element, it's not necessary. Okay, here we started with a random stream. We need to simulate in this problem. So set seed 1, or we could write 1 2 3. Kind is Mersenne twister. Okay, and variance sigma square is 1. I think that's also given in the problem. 0 means sigma square variance. Coming from here I'm sorry, coming from here we are presuming the variance is 1, and log likelihood function is by sigma square minus 0.5 y minus m square divided by sigma square, because this whole part represents m, so y minus m square divided by sigma square, the regular equation, and we want this to return LF. This is a pretty good thing in R which specifies what is to return, because in MATLAB it creates some confusion sometimes, because we want LF to return we want neglog function to return LF whenever we're running neglog function. However, it is very easy in R to do that, because it don't let you forget that you are returning log likelihood function. Now let's move into the regression model. 100 is the observation, number of observations. First we need to simulate data with given theta equals 2. Let's have a look. Given is theta equals 2 plus mean is 2 plus random uniform distribution, random t rows 1 column, t run if 2 plus run if t 2, because the mean is 2. U on the other hand has a random number run if and R norm. Why? Because here it mentions that exogenous variable has uniform distribution, but the disturbance term has normal distribution and not uniform, 0 and sigma square. So random number t1 R norm, so run if and R norm, y equals 1 by x minus theta plus u. This is simply the equation. With that we generate y, values of y automatically, then start 1.5 given mean, gradient is mean y minus the equation's portion. This is the value of u actually, y minus 1 minus start multiplied to 1 minus x start square, right? This multiplied to the term squared. Okay, so basically y minus this minus squared is method of scoring. Okay, so we are doing scoring algorithm here. If we can recall, scoring replaces negative Hessian with information matrix, and theta becomes theta k minus 1 plus gradient divided by the information matrix. So mu by sigma square is the function, and there are steps. First, what is the step? the first step is then the step 2. Okay, first step is to find the log likelihood function, then the variance. So we discussed all of these earlier. So basically then mean is squared, this one, and squared because, well, we're talking about a gradient, and how do we measure gradient? Let's see. Because we're measuring gradient is this, right? This is the gradient portion of a log likelihood function. So this is what we are representing, gradient, and information matrix is to the power 4. Well, it's very hard to keep track sometimes, just to remember with method of, I think this is in general 1 minus well, x portion, the second element, then multiply the second element being squared, because we are doing differentiation here, and then information matrix, again doing further differentiation. We are left with 1 minus x star to the power 4. Okay, theta 1 is the initial value, theta naught plus gradient divided by information matrix that we have just seen. It's a method of squaring starting value of theta, updated value of theta. Fine. Estimate the model using BGS and compute Hessian. This time we just need to run the optimization for calling the function, and we need beta hat and Hessian, and then we have variance covariance matrix, which is inverse of Hessian divided by T. That is all. So the little puzzled we were here with gradient, which is mean of y minus x minus theta multiplied to y minus x minus theta whole squared, because I think, yeah, because we did differentiation in gradient. Exactly, because we did differentiation in gradient, because gradient requires you to take the first difference of mean with alpha and with beta. So here we don't x minus theta, we're doing it for theta, and so we have, this is coming again and again. Information matrix on the other hand is also the same, is simply a information matrix is expected Hessian. So we are doing the taking the differentiation further. With taking further differentiation, we are left with that. So that was nonlinear regression model. Okay, see, y minus beta naught exponential multiplied to beta naught exponential xt and xt. You see, this tells how the gradient for the beta is going. Okay, beautiful. And this part is being squared that we need, I think, for Hessian, so becomes to the power 4 Hessian beta hat. beta naught and beta 1. Okay, great. So there you go. First equation, first problem we have gone through. Then the second problem is regression 1. Consider the nonlinear regression model. Again, oh no, we have already, sorry. Consider the nonlinear regression model given by beta naught plus beta 1 xt plus ut. Just have a look through the problem, giving you some time to look into the problem. X is exogenous, y is the dependent variable, mu is the disturbance term, theta is beta naught, beta 1, beta 2, sigma square. Using the transformation of variable technique, derive the distribution of y and hence the log likelihood function. So basically we need to derive y and log likelihood function value. We need to do Newton-Raphson, B triple H, Gauss-Newton. Then we need to do 100 simulations with the given beta naught, beta 1, beta 2 sigma square values, where exogenous variable is IID chi-square. We want to find concentrated sigma square from the log likelihood function, and then we need to, it is a combination of all the things we did before. Yeah, this problem should be very similar to this problem should be very similar to this. See what this, in this what we had, in this problem what we had was, first what was given to us. First there was a production function given to us. We took out differentiation on this. Then we concentrated out the conditional density function from linear. So did quite a lot of stuff here. We need to borrow some of the steps from here, I guess, to solve this problem. So have a look. Let's see if we have any. Yeah, we have a local function. First, the regular log likelihood function b1 plus b2x is the problem. How is it specified? Let's have a look. b1 plus b2x. Residual is, this is m, that portion. Residual is y to the power beta 3, y to the power beta 3 minus this portion, indeed, simply stated, that's all. Then concentrating the log likelihood function, concentrated log likelihood is sigma square is the regular, u square by t, and then log of beta 3, log of beta 3 plus beta 3 minus 1 into log y minus 0.5 u square by sigma square, log of beta 3 to 3 minus 1 into log y. Beta 3 minus 1 okay, because yeah, beta 3 minus 1 into log y. This structure is similar to this structure. See, this This was the equation, right? Then log of beta 3 minus beta 3 minus 1 minus the rest, u square by sigma square. So in between, because of beta 3, we have these two portions. Alright, basically if we take the log likelihood function on the equation, then we are left with that's all. Log of beta 3 minus 1, so basically this equation, and then we specify the parameters, we generate the data, and then we calculate y and then we simply do optimization. There is no tricks here. That's all. We want our information to come as real values. So basically that is it. Now we are going to look into some of the very practical applications, such as testing for liquidity trap. The problem suggests the data file contains monthly data on money, real output, consumer price index, and federal funds rate for United States from January 1959 to December 2011, about 60 years of data, 50 years of data. Considered the nonlinear money demand equation used to model a liquidity trap by Constance and Khuja, given by y equals beta 1 x1t plus beta 2 divided by x2t minus beta 3 plus ut, where the residual is IID with normal distribution, zero mean and sigma square variance, in which y is the logarithm of real money, log of real money, x on the other hand is the logarithm of real income, x1t, x2t is the nominal interest rate, ut is the disturbance term, and theta equals unknown parameters of beta 1, beta 2, beta 3 sigma square. If beta 3 is greater than 0, then as the interest rate x2t falls towards beta 3, the semi-elasticity of the interest rate approaches infinity. If beta 3 equals 0, there is no liquidity trap, and the model is linear in exogenous variable. So beta 3, if the interest rate falls towards beta 3, the semi-elasticity of the interest rate approaches infinity. That is what liquidity trap is, and it is linear if beta 3 equals 0. Construct world LM test for null hypothesis testing with beta 3 equals 0, and estimate model by maximum likelihood where sigma squared is concentrated from log likelihood function. Test for liquidity trap using the statistics derived in part A. Interpret the results. So analyze liquidity trap. So that is the problem. There must be some local functions. Yeah, the log likelihood function to estimate. So we have unknown parameters beta, y, x1 and x2. This is the equation. Y equals y minus beta 1 x1 plus beta 2 x2 by beta 3, and sigma squared is u square divided by t, as we already know. No tricks here, simply as we need to remember the arrays come in third brackets in R. The log likelihood function on the other hand is simply given as it is, log sigma square y minus mean square divided by sigma square. That's all, very simple. Here the mean is the second part except for y. So y minus, basically it's not mean, I'm sorry, this is the whole equation, square divided by sigma square. Then let's go to the main problem. First we need to, there is no simulation, so first we need to do remove object, which is all equals true, is all true, least equals is and rm, and graphics of. Then we need to load the package, then we need to load our variables, where the first data is coming giving us consumer price index, then the second is GDP, third is interest rate, M2 is 4, which is real money or money, yeah, right. What was M here? Monthly data on money. So first let's construct the variables. Y equals log of M2 divided by log of M2 divided by consumer price index. X1 is log of GDP, X2 is interest. So money against consumer price index, that is Y, right? Because yeah, we'll go one by one slowly. So estimate linear model by OLS. First ones, then x1 and x2, then we do the regression, then we do the residual, then we do the sigma square. Okay, so first column bind, these are coming in columns, no, they are coming in rows actually. They are coming in columns. Column bind, repeat matrix 1 to t. So basically we want everything in one column, all the values of x coming in one column. So that's column bind. Row bind is coming in one row. So once x1, x2, then we are doing the regression. See, because linear model regress y on x minus 1 coefficient. We are taking the coefficient values only from this regression. We are just putting the coefficient values in volts, then y minus x volts, and then sigma square. Then two-step LM test, stage 1 regression. Again, what were our situation with the equation? Once x1, 1 by x square, 1 divided by x square. This is simply, yeah, x1, 1 divided by x square. 1 divided by x2 square, 1 divided by x2, not squared, 1 divided by x2. Then beta 1 is the regression, then residual. Okay, just like that. Then stage 2 is z, which is x 1 divided by x2 squared, because we are doing a differentiation. It's very easy to remember. The element comes as it is, then the element is squared, that's all. Then we are doing u, regressing u on z. First find z, then regress u on z. Z is first as it is, then the squared portion comes in. We always have to remember it, which is because this is differentiation, nothing else. Then v is u minus z into b2, u minus z into ZB2. So this is the updating scheme. V and R square is 1 minus VV transpose divided by UU transpose, as we have already seen before, and LM. So first step is to make a regression, make a differentiation on this, right? So the first term is as it is. I think this is in terms of 1 by mean and variance. This is in terms of beta 3 x1 by x square. By the way, do we remember how to find z's? Let's have a look. If we can just quickly have a look. Okay, my god. All right, basically this is how we find the z's in two-stage regression models. First, for beta naught, see, it's 1, so that's why z1 is always coming in ones. Then for beta 1 is differentiation on beta 1 portion. Then beta 2, which grows, which becomes bigger. And in this problem, hence in this manner, first beta 1, then beta 2, then beta 3, isn't it? Yeah. So first we did beta 1 is already regressed, x1 1 by x squared. Then in stage 2 we are focusing on not the ones anymore, but beta 2 and beta 3. See, and then we evaluate ut, and then we update delta. So first the function, then we do yt beta 2, then log of yt. That's how it comes in. That's why first when we regressed on beta 2, basically there was nothing. Then when we regressed on this, then it became squared x2t minus beta 3 1 by x2 squared, just that, nothing else. So then the next part is to estimate the model. (213) is the given information. From the given information, either from the given information or from the estimation parameters. And then just do what you regular do, optimization. Hessian is also mentioned here. We are finding Hessian as well. So here, see, we want to find Hessian in the same optimization. So after method we don't end, we mention that we want Hessian as well. Hessian beta hat all, we can do it all in one go. Beta hat 3 minus 0 square divided by VC33, third row, third column, vertex beta hat 3 minus 0 squared. Okay, so we basically did what is asked from us to do. Okay, there you go. Now this liquidity trap is done. Then the next problem, Young's non-nested test of money demand. Okay, so the problem on money demand suggests this exercise is based on quarterly data for United States on real money, the nominal interest rate and real income. for the period March 1959 to December 2005. Consider the non-nested money demand equations given by MT beta naught beta 1 RT beta 2 YT plus U1T, then log of MT equals alpha naught plus alpha 1 RT alpha 2 log YT U2T. Estimate model 1 by regressing M on C, RT and YT. Well, real money, real interest rate and the consumption function, and construct the log likelihood at each observation. Log likelihood function is given. Estimate model 2 by regressing money, log of MT on C, log on T, and construct the log likelihood function of transform distribution. Perform Young's non-nested test and interpret the result. Let's see what that is talking about. Actually, I don't think this is difficult. So there are two likelihood functions that we need to mention. First is model 1, simply the log likelihood function from the given equations. Put them in here. There is basically no trick at all because these are already given to you. You just need to jack the log likelihood functions inside here. That's all. This u square by 2b4 plus, yeah. Still have a look. Square by 2b4 minus log MT. So basically, these are the equations. So beta 4, log of beta 4, log twice y. Well, log of beta 4, then u squared divided by 2 beta 4 plus log of absolute value 1 by expected value of y expy. What is exp? Well, let's see. Oh, exp is exponential of y. I'm sorry. Exp is exponential of y. So basically, sigma square, half log sigma square, then half log over sigma square. We are representing sigma square as beta 4 because we want our system to estimate that. Then we are seeing u square because this whole thing is u. So u square by 2 beta 4 plus log of absolute value plus log of absolute value of 1 divided by exponential of y, because log of MT is this, right? So we are just doing exponential of y, 1 divided by exponential of y, or is it regressed upon? No, absolute value of 1 divided by exponential of y. So after this is very easy. Then the whole MT comes in because MT has the equation, all right, which is this part, right? Oh, because this part requires logarithm, log of absolute value of 1. This part is log MT. This is MT, this is log MT. So exponential of y. Okay. Each observation. Let's see what is the test. So first we bring in data. Simply money is divided by consumer price index. GDP is divided by consumer price index. Treasury bill. We fix the data first. There is nothing to explain. We simply fix the data. Then we estimate the model. Y equals empty. Then x is 1s. Then rt yt. Regression. Sigma square yxb transpose multiplied to yxb u transpose divided by t. Simply we are doing it in all in one go. You see here we are doing it all in one go. That's all. And so model 1 LF1 is model 1 is we are just calling the function. See, we are just calling the function, but we are not running any optimization. We are just calling in LF1, we are just putting in the log likelihood function because we did all these estimations. Now we are putting all the information in model 1, and so we have a log likelihood function value because we want to do a likelihood ratio test. That's all. Estimate model 2, log of MT, same thing, same. We estimate the models as before. Then we simply call the log likelihood function. Here see column. We are putting these in columns B under B sigma squared because we want this to be in one column. So column, we are putting this in one column. That's all. There's no tricks in here. And the Vuong's test is simply LF1 and LF2 without optimization. There you go. It's very simple. And in Vuong's test and the p-value square root of v square root of d bar, well, mean divided by standard deviation, square root of t multiplied to mean divided by standard deviation, normal distribution. We want normal cumulative distribution. So p norm v0 1 is the well, p norm v01 norm CDF v01 is simply, I guess, let me check though. All right, alright, let's just wait for MATLAB to return. As you can see, V is what is to estimate the whose distribution we want, mean and sigma. So that's all, very simple. So V 0 1 0 mean 1 variance, V is what we are finding of. So P norm, that's all. So very simple and easily solved. There you go. In this chapter we have two more problems to solve. One is a KPM problem, another one is a stochastic frontier model problem, but as they are very theoretical right now, we are not gonna solve it. Rather, we're gonna take a small break from here, and later on we might come back and discuss KPM and the stochastic frontier model in further detail. Thank you for sparing with me. And you see, I need to mention here is that this is a revision process for myself, and not necessarily I'm an expert in MATLAB or R, and sometimes obviously applied econometrics is difficult. Sometimes I get stuck when I'm trying to explain, so I hope you will look into this with much more leniently, as I'm not an expert educator. I'm hoping that further with progressing further, the chapters ahead will be easier. In this chapter we learned some very important stuff like the process, the steps to regress U on Z, because the Z estimations, Z's will be estimated again in coming chapters, where you will be regressed on Z. There will be two-step method LM tests that will be applied again and again. So these things will come back again and again. Thank you very much.